Welcome. Thank you all so much for coming. We were a little nervous this time yesterday with the weather, hoping the snow and whatever else was going on, sleet, would kind of behave and go away, and it seems to have worked out. So thank you. Welcome to the Du Bois Library, University of Massachusetts Amherst. My name is Simon Neame, and I'm the Dean of Libraries here, and I'm very, very pleased to welcome you all. First of all, I want to say a few thank yous to the folks who are behind this event today, A Climate for Change, University of Massachusetts Sustainability event. First of all, to some of the folks who worked behind the scenes to put on this event today, I'm just going to list a few names here. Madeline Charney, Carol Kinnair, Kim Phil, Allison Corrali, Leslie Shaler, Cheryl Crow, and a number of students who are helping us today, and others who work in the library and do fabulous work behind the scenes. I'd also like to say a huge thank you to all the participants in the Sustainability Showcase. I hope you all got a chance to see that amazing work. The faculty, graduate students, and undergraduate students who are doing incredible work around sustainability on this campus. We really wanted you to have a chance to meet the students and faculty who have propelled our campus to be rated one of the top 50 most environmentally responsible colleges, according to the Princeton Review's Guide to Green Colleges. Yay. So our campus was chosen for its factors like alternative transportation options, use of local and organic food, our formal sustainability committee, and the availability of a sustainability-focused degree program. 25 of nearly 90 undergraduate majors are sustainability related, while more than 300 courses include a sustainability emphasis. Also, 3 new graduate programs encourage advanced studies in sustainability, including an accelerated master's in sustainability science. Also noted was the Eco-Rep program, which I was just talking a little bit, yay to the folks behind that fantastic program. And also the Permaculture Initiative, a program that creates educational and edible gardens across campus. Hopefully you had a chance to meet some of the people making all this wonderful work happen during the showcase. We're also here today to acknowledge and celebrate the generosity of donors to the Sustainability Fund. Started in 2011, it has reached a total of more than $350,000, which underwrites everything from the purchase of books and films to speaking programs and workshops. Like many library initiatives, it is our donors who help us reach our goals and meet student needs. So a big round of applause. First official task today is to introduce our first speaker. I would like to introduce Madeline Charney, who is a research services librarian here at UMass Libraries, who is with a focus on sustainability. We really call her our sustainability librarian. Madeline spearheaded the Sustainability Fund after returning to campus following a sabbatical focused on how libraries can support sustainability. She has become the go-to person connecting sustainability communities across campus and is always ready to collaborate, assist, connect, and demystify in order to achieve the greatest impact. Now, Madeline's making news beyond UMass. In 2013, she co-founded the American Library Association's Sustainability Roundtable, Libraries Fostering Resilient Communities, which successfully proposed the groundbreaking resolution on the importance of sustainable libraries. More recently, and we're very excited about this, Madeline is the winner of the 2017 Library Journal's Movers and Shakers Award, which profiles individuals from around the world who are innovative, creative, and making a difference, and celebrates the people moving all types of libraries forward. Above all, Madeline believes that libraries, whether academic and otherwise, and sustainability go hand in hand. So please join me in welcoming Madeline Charles.
Thank you, Simon. It is a privilege to work here, and I always tell people it's so exciting because as librarians we don't work in silos. A lot of people in academia lament how they feel isolated in their departments. We feel great. We're helping everybody, and sustainability is so interdisciplinary that the work that I do here really is so highly collaborative with all my colleagues here in Du Bois and also the Science and Engineering Library. And this year we've continued to do a lot of sustainability projects. We're co-sponsoring talks all the time, this year with Divest UMass and Women, Gender and Sexuality Studies. We had a poetry reading with Don Ogden, who wrote the now pretty famous book Bad Atmosphere. We had a career workshop the other day for students to help find their life purpose. These events are often under the auspices of Talking Truth, Finding Your Voice around the climate crisis, which is again a highly collaborative project on campus with many departments involved, but hosted mainly here on the 26th floor of Du Bois. And we had some film screenings, we have had some author talks, all really well attended with a lot of excitement. Students, faculty, staff, community members are all welcome to join us at these library events. And of course, the fund has helped to sponsor so many databases, books, media that help to fuel the research of our faculty, students, and staff, as well as the community. And you'll hear in a moment about the Undergraduate Sustainability Research Award, which is really great evidence of the work that our students are doing around sustainability across disciplines. So, having said that, I'm on to announcing the award winners. Is Donnie Rollins actually here? He's one of our... You are here! Okay, great. I'm going to let everybody know about this, the first place award. So the Undergraduate Sustainability Research Award is now in its third year, and this year first place goes to a team. They wrote a project called What Is It Going to Take to Make Solar Panels Cool? And Donnie Rollins will come up in a moment. He was also on this team with Cameron Lane, Luke Fatager, Cameron Smith-Friedman. I'll just say a moment about the project, a small abstract. Solar panels operate more efficiently at lower temperatures and when clean. This paper proposes a system of collecting rainwater so it can be reused to cool and clean the panels, thereby improving their power and output by at least 15%. This year's winning projects, besides the one that we're about to award right now, will all join the previous year's winners. They become part of the library's special collections and archives, as well as entered into ScholarWorks, which is the university's digital repository. So the first place winners will share a $1,000 scholarship that was underwritten by the library's sustainability fund. And before I go on and give Donnie the award, I also want to mention second place went to another group that did a project called Proposal for Implementation of an E-Receipt System and Non-Toxic Compostable Receipt Paper at the UMass dining facilities. These are really innovative, cost-saving, and carbon-reducing projects. Another second place went to Sam Kefferston. His paper was called The Perfect Storm, Lasting Impacts of Structural Adjustment Programs and Pressures of Climate Change in Latin America and Ghana, Africa. And finally, an honorable mention went to the Biosted Initiative, which was a project to construct safe-to-fail green buildings as sustainable development research sites on university campuses. And when the review team read these awards, it's so heartening every year just to see the depth of analysis, the commitment to these topics that the students take on and really are showing their best. So thank you. And Donnie, if you'd come up, I'd like to give you the award. Solomon Goldstein-Rose, Representative Solomon Goldstein-Rose. But first I want to say a few words about a recent Yale University study. They have a climate change communication program at Yale, and they recently published the studies of a national survey that revealed this spiral of silence around climate change. So that it showed that people don't really talk about climate change, even as they acknowledge so well about this urgent global matter. Representative Solomon Goldstein-Rose is urging us to have those conversations. And as Albert Einstein once said, we can't solve problems using the same mindset that created the problems. And climate change certainly is a wicked problem indeed. Representative Goldstein-Rose keeps inviting us to talk about it. We were delighted here at the library when he came to one of our Talking Truth sessions. Every Monday we get together, we call it Holding Earth Mindful Climate Action, and he showed up. And he's showing up in coffee shops and community centers and inviting people to keep talking about climate change and what to do. So when he walks those hallowed halls of our State House in Boston, we can know that he's also walking in our shoes and giving voice to our power, our clean energy power. And for that, we would like to give him the Sustainability Hero Award for shining a spotlight on the real cost of fossil fuels, for educating us about the need to put a price on carbon pollution in Massachusetts, and for illuminating ways to invest in businesses and clean energy job creation rather than wasting our money to buy out-of-state oil and gas. What is sustainability? There's so many definitions. We're debating this all the time. I really like the definition that it is the capacity to endure. And what is a hero? Someone who leads, inspires, and gives of themselves. And for all these reasons, we find you very deserving of this Sustainability Hero Award.
This is by far the prettiest award I've ever seen. I won't say the prettiest award I've ever gotten, because I haven't gotten many, so. I will admit, I think it's a little preemptive, given that I've only been in the legislature 3 months, so I appreciate the vast confidence you have in my ability to get things done. I'm really grateful for this, and I was talking with some of the people before about this guest column. I'm doing a monthly column in the Bulletin now, and this month's was about a bill I've introduced on clean energy jobs. I'm calling it the Energy Jobs Bill, and it is, as Madeline mentioned, trying to highlight that intersection of the need for new technologies to provide energy cheaper than fossil fuels as an economic development for opportunity for Massachusetts, and as the biggest way that we can contribute to solving climate change. And I use the line all the time, we're not going to ask a poor farmer in India to forego a coal power plant that's raising millions of people out of poverty, billions of people out of poverty worldwide. We have to have something that's actually cheaper. And we can develop that in Massachusetts. And we can do that while creating economic development in our state, new jobs, high-tech manufacturing, all sorts of good things that we would like to have in Massachusetts. So that's what the bill is about. And it includes carbon pricing and some other structural things. You can get more info on it at solomongr.com if you want. I won't go into the details now, but thank you all for being here. And I wanted to stress the importance. I was playing around with a climate model earlier today that's some UMass Lowell faculty put together. And the number of things we have to do to get anywhere near staying under that 2 degrees Celsius target, it is scary for me, anew, even though I've worked on this for years. And so how many of you consider yourself a climate activist of some sort? So we've got a lot of people here, and not everyone has to be. Everyone needs to find their way of contributing in the world. Not everyone's going to be good at being a climate activist. Maybe other issues you can speak better to. But if you didn't just raise your hand, I want you to at least consider pushing this issue with people who might not care about it as much, especially if you have friends in other parts of the state, other parts of the country. We need more conversations about this, and we need more productive conversations about how this is not just the biggest crisis of our time, which it is, but the biggest opportunity to create new jobs through new technology, to be innovative, to be creative, and to work together for a clean energy future. So thank you all so much. Thank you for being here.
Great. Well, congratulations again to Donnie and all the students, and to you, Solomon, for those acknowledgements and awards. And thank you again, Madeline. So, the next task is to introduce our two speakers for today. We have two leading climate change experts here at the University of Massachusetts, and I'm really excited that they are here today to talk a little bit about their work. I'm going to start with introducing Dr. Julie Brigham-Grette, who is a professor of Quaternary glacial geology and Arctic paleoenvironments, and is a department head of geosciences here at UMass Amherst. Julie is also the chair of the U.S. National Academy of Sciences Polar Research Board and was named 2016 Fellow of the American Geophysical Union, an honor given to individual members who have made exceptional scientific contributions and gained prominence in their field of Earth and space sciences. Her research focuses on the chronology of geologic systems that record climate evolution and sea level history of the Arctic over the past 3.5 million years, and on documenting the global context of ancient environmental change across the Barren Land Bridge. Julie has recently been named a Public Engagement Faculty Fellow by the Public Engagement Project, a UMass-based initiative which supports and trains faculty members to use their research to contribute to social change, public policy, and to enrich public debate. I'm also going to introduce Rob as well at the same time, and then they're just going to do their, both present, and I think they're going to tag team a little bit, and then there'll be questions at the end, an opportunity to ask questions. So it's also my pleasure to introduce Dr. Rob DeConto, who is Professor of Climatology in the Department of Geosciences here at UMass Amherst, and is one of the world's leading experts on polar climates, ice sheets, and sea level rise. He is the winner of the 2016 Tinker Muse Prize for Science and Policy in Antarctica. This recognition comes from his outstanding work on past and future Antarctic climate research and for integrating geological data and modeling to reveal likely consequences for the future sea level rise from ice sheet melt. Rob and co-author Penn State climate scientist David Pollard's March 2016 paper in Nature, Contribution of Antarctica to Past and Future Sea Level Rise, was named the most featured climate change paper in the media last year, as reported by carbonbrief.org, which is a UK-based website covering the latest developments in climate science, climate policy, and energy policy. So please join me in welcoming both Julie and Rob.
So we've got this mic on.
Yeah.
And I will speak really loud so you can hear me really well. So thank you so much for coming today. And I'm going to use this opportunity to share with you kind of the perspectives we have on climate change, and certainly some of the roles that we at UMass have played in that. First of all, I want to just give you some perspective. I'm a geologist, so I think of myself like a time lord, in the sense that I study past change. And this graph down here goes from 5 million years ago up to the present at the far end. And when it goes red, this is warmer than present, and blue is colder than present. And so I like to look, what I study, what my research is in, looking at how did we go from a forested Arctic back at this time period when we had no Greenland ice sheet, There was a waterway between the Pacific and the Atlantic. And how do we go from this world when we think carbon dioxide in the atmosphere was in the range of 350 to 400 parts per mil, more or less like today? And then how did we go into this glacial, interglacial world? And how did we get there? And of course, today, we're back heading ourselves into this world, and what are we going to do about it? What are the consequences? So I really like to think of myself as kind of a Time Lord, and if you watch Doctor Who, you all have your own favorite Time Lord. This is one of mine. So I've been working for almost 40 years in the Arctic, and one of my favorite ideas is just thinking about going from that forested Arctic to the present. So I recently ran a big project in northeast Russia here at Lake Ilgagikin, where we got a sediment core record that went back 3.6 million years. And it was amazing to find this record from the high latitudes that tell us so much about what the climate was like in the past. And what we learned was, in fact, the Arctic was warm in the past. We have a lot of evidence, even who knew that camel originated on Ellesmere Island 3.5 million years ago. So we have this very unusual world that a lot of us can't even imagine, and yet we know that the higher latitudes were very warm. So where are we going today? What's happening today? How are we today driving the Earth system toward that warmer world? We'll take questions at the very end.
Refer to that particular slide. What do those numbers indicate?
She's going to finish that.
I'll finish the slideshow and then we'll come back to that, okay? So how do we heat up the world? How do we make the world warmer? We make the world warmer for glacial, interglacial changes by changing the shape of the Earth's orbit around the sun, the tilt of the Earth, and the season in which we're closest to the sun. So that's long, long time scales in which we can change the temperature of the Earth. But the other way we can change the other way we can change the temperature of the Earth is by changing greenhouse gases, the carbon dioxide in the atmosphere. And so this diagram is from the NOAA website. Some of you may have seen it. But what's tracking here in this map are two sites. The blue one here, down here, is in Antarctica, where we're measuring carbon dioxide and fossil air over time. And then here are measurements of CO2, or this is measurements from the air and also from Mauna Loa here. And what you see are all these different sites recording carbon dioxide in the atmosphere. What you notice is also that it wags back and forth. And this is the northern hemisphere seasonal cycle of spring and fall, winter, spring and fall, when we undergo through photosynthesis, which takes CO2 out of the atmosphere, and then decomposition that puts CO2 back in the atmosphere on a seasonal cycle. And so what we now are going to do is take this record that's been measured from these sites and go back in time, and I'm going to attempt to stop it. Okay, so somewhere around here, I want to make a point that this is where my grandmother was born in 1895. Somewhere around here is when my mother was born. My parents were born in the 1920s. Somewhere right here is when I was born in 1955. And somewhere around about here is when my two sons were born. They're both 23 and 26 years old now. This is where we are today at 400 parts per mil. So we've seen this rapid acceleration in the carbon dioxide in the atmosphere. So just to give that some perspective, and now start that again. So now what we're doing is going back into the ice core data, fossil air preserved in the ice cores in Antarctica and also in Greenland. We're going to go back through time. Now we've gone back, and as this starts to unfold, we're going back to the last ice age, and then back to the last interglacial, the last warm period, and then the previous glacial, interglacial, glacial, interglacial over time. And we can go back 800,000 years and see that the normal range is about 180, 280, 180, 280, 180, 280 for CO2 in the atmosphere. We are up here now at 400 parts per mil. So we're way outside of the normal box. And you can see from this graph, which I just grabbed off from the internet yesterday, so it's hot off the press here, shows you the normal cycle of decomposition and photosynthesis through the year. But one of the things I want to make a point here is that last fall, when CO2 should have been the lowest possible level, the lowest possible level of the seasonal cycle, we were well above 400 parts per mil. So my point is, for the rest of our lives, we will never be below 400 parts per mil again, unless we do something. So we've reached an important threshold that really is pretty critical for us to think about what happens when we get above 400 parts per mil in the atmosphere. And of course, what we can see is most of the whole world is warming, with the highest warming, of course, in the high latitudes. This is a temperature anomaly that's averaged over for example, if you think about the first 30 years of my life as an average, this is how much the temperature has warmed in the second 30 years of my life. So we're really seeing this warming on a global scale, of course. And this figure is also from NOAA that shows you also the seasonal from January to December, how temperature has changed over the period. And you can see, of course, we met an incredible landmark in that 2016 was the warmest year ever, and 2015 was also warm, 2014, so we just keep sustainably maintaining this very, very high temperature anomaly. So what's that doing to the Arctic? What I see is as the tree line is moving northward, the Arctic is getting greener, and we also see, of course, that the classic is the sea ice is getting less. When I was doing my dissertation work in the 1980s, I got stuck in the sea ice. I had to get flown out. I had to get food and fuel flown in. Now, I wouldn't have that problem because there's not much sea ice. The thicker sea ice, multi-year ice, is here in white. And what we've seen over the last few decades is a massive decrease in the thick multi-year ice. So we now have mainly an Arctic that's one-year ice that's only about a meter thick. And so it makes it very vulnerable to change over time. So this has been a really important. And this is that I picked up today. Shows you where we are, and this is, we're approaching in the next month or two the maximum amount of ice for the winter season, and this is now the lowest record maximum, if that makes sense. So for the winter, it's the lowest maximum ever that we've seen. So we're getting into critical zone, and we can obviously see a lot of things happening in our world with excessive droughts, increases in the number of days well above 100 degrees, not only in India, but in our own country. We have excessive rainfall in parts of the UK, massive flooding, and of course drought or extreme snow, like we had in Boston. So we've got weather weirdness, we've got climate change weirdness, for example. You might think of it that way. So why is that? If that's all happening in the Arctic, what's it mean to us? We're down here in the lower latitudes. What is it going to matter? So just a little bit of climatology here really quickly. Here is a cross-section of the atmosphere from the tropics to the polar regions. And you can see that the thickness of the atmosphere in the tropics is thicker, it's warmer. And as we descend down toward the thinner atmosphere in the polar regions, we can think of the heat of the tropics getting transported toward the polar regions to help balance our planet. But what's happening is that the Arctic is warming up. The tropics are not as warming up as much. But here you can see a little cross-section, pardon my cartoon. Here is the thickness of the atmosphere in the tropics. Here it is in the Arctic, and you see a gradient here. So here we see a very cold high latitude and a warm tropics. But what we're seeing now is, in fact, the equator is warming maybe a little bit, but the Arctic is warming a lot, changing the gradient. And if I can maybe go back and forth, so you can see how that tilt changes the gradient from the North Pole to the equator. So what that's doing, some scientists think, is that it's actually changing, of course, the way the polar jet responds. And so this gradient is making the polar jet, as you see here, wave across the planet. And you can see that it's getting more of these waves. We keep getting more of these types of wavy plant forms in the upper atmosphere. So instead of going straight across at higher velocity, we have a wavier pattern, more meandering pattern, so that weather patterns tend to get stuck. So we tend to have this really cold air coming down here in New England, and unfortunately hitting Washington, D.C., where so they don't think that they throw snowballs in the legislature, right? So, whereas in fact, what we're seeing is possible consequence, so that what's happening in the high latitudes is in fact changing variability in our lower latitude weather systems. And of course, with that, we see glaciers starting to collapse. Almost all glaciers are in massive retreat. This is the Columbia Glacier that has retreated on the order of about 20 kilometers since 1980. There's some time-lapse photography from Jim Baylog at University of Colorado. And we also see that parts of Greenland are also melting very quickly, reaching these with massive losses here in these areas in red, tracked over time. And Rob's going to talk to you a lot more about ice sheets and also about projections for sea level. So I'm going to put that on the table for a minute and let him tell you about that in a little bit. But sea level is important because we have a lot of real estate at sea level. Sea level's been stable more or less for about 5,000 years. We got used to it. We built our cities there. We built our infrastructure there. And suddenly now sea level is rising again because of what we're doing to the atmosphere. And we have a lot of coastal cities and, of course, large communities in these areas. And, of course, we're constantly having to rebuild because we're tough Americans. We're going to rebuild. We're going to make it work, right? That's our mentality. But maybe that's not the best idea. We need to think about that. We hear about what Florida is kind of a canary in the coal mine on this. Northern Florida doesn't want you to talk about climate change. Southern Florida is ready to kind of annex themselves from the rest of the state. And so if you just look at how these very low-lying areas are really in trouble, and worse recently, during a king tide, they actually had an octopus. It was very wild on the internet. The octopus that came up the storm drains and ended up into the parking garage of one of the local condominiums there because there's salt water now flooding the streets in parts of southern Florida. So if you just take a look at this, this is of course this famous property we all know about, and this is showing you how much of that area is submerged under 3 feet, about that much sea level rise in the future. And if we go to 6 feet, we have about that much. So if we toggle back and forth, you can see how many, not only this property, but a lot of other people are going to be in trouble. And if you have a 30-year mortgage on your property, who's going to pay for that? And here's just that same, how we were looking at West Palm Beach here. This is the rest of Florida at 3 feet, and here it is at 6 feet. And Rob's going to talk to you about what's going on between 3 and 6 feet in these scenarios. What's also we've got to get our heads wrapped around is how do we manage retreat? How do we realize and get people to think, oh gosh, my grandmother lived in this house all these years at the coast, I'm going to rebuild. But maybe we can't afford that. How do we wrap ourselves up? It's a difficult thing. Nobody wants to lose their property. But we may have to think about that. It's mind-boggling. This is the Miami coastline today. And this is a new property right at sea level that they're proposing to build. Someone is paying the real estate companies to build these kinds of high-rises right in harm's way. So why would you have a 30 or 40-year mortgage on a building like this? Probably is going to have seawater in the front door by the time the kids who are in Fort River kindergarten today, by the time they're 80 or 90 years old, this will be flooded. So it's not that far away. We need to think about that. There are feedbacks going on that we need to watch for. So geologists are working very steadily at looking at these feedbacks. And one of them is as we warm the Arctic faster than we warm the globe, we're also releasing a lot of methane. And methane is also a very toxic greenhouse gas. So this is something that many of us are poised and worried about. How this is going to amplify the warming that we already have. And this is just to show you how this methane is accumulating under the ice in the lakes. This is methane lit from under the ice in the lakes, it's entrapped. And I want to put a pitch in. The woman lighting that is Katie Walters. She got her master's or her undergrad degree at Mount Holyoke College. And now she's a professor at University of Alaska. So there are other feedbacks going on. We have more fires because of aridity. We have more people using stoves that put out a lot of carbon. This carbon goes up to the high latitudes and ends up on the ice sheet, producing darkening the Arctic, increasing the rate at which it's melting. I was just with a National Academy group. We visited central Russia a year ago, talking to the Russians about black carbon. And they do talk about it. But they're in a difficult situation too, because they are in the middle of a cold country. Yeah. So I just want to make a couple of more points. So about 18 months ago, countries from all over the world met in Anchorage, Alaska, to talk about carbon emissions, the Glacier Conference. And President Obama, at the time, borrowed a phrase from Martin Luther King. And I want to mention this because we're in the Du Bois Library. There is such a thing as being too late. And when it comes to climate change, that hour is upon us. So I want to throw in this quote. Here's a quote that says, "I put my money on the sun and solar energy. What source of power? We hope we don't have to wait until the coal and the oil run out before we tackle that." Now, who said that and what year? Does anyone know? Du Bois and Jimmy Carter. Well, guess what? Thomas Edison, talking to Henry Ford and Firestone in 1931. Wow. Wish we'd thought about that earlier. So we have a great number of people with solar panels and wind generators. There's a lot to be optimistic about. Clean energy is generating more jobs than the coal industry ever thought about. And I just want to put that in context. So this is Martin Luther King's comment at a different time for a different reason, but very real today for both not only racial equality, but also for climate change. We are now faced with the fact that tomorrow is today. We are confronted with a fierce urgency of now. And in this unfolding conundrum of life and history, there is such a thing as being too late. There is no time for apathy or complacency. This is a time for vigorous and positive action. Thank you very much. Do you want to use this? Yes. You want this in there?
That's okay. I can use the mouse.
Okay. Oh, we don't want to mess with that now. Okay.
Always a tough act to follow, being behind Julie. That was really great. After the introductions, I just wanted to quit while we were both ahead.
I turned this off. So,
Oh, you did?
yeah. Toggle the top of it on. Yeah.
Sounds better. This is working. Yeah, great. Okay, well, thank you, and thank you, Simon, and thanks to the library for hosting the event in general, and to invite both Julie and myself to come talk about climate. So, great setup from Julie for me. I am mostly, over the last 10 years, I've been working on sea level rise, and mainly thinking about the big polar ice sheets, and I'm going to show you where the big ice sheets might actually end up really strongly influencing our future, including here in New England. So Julie showed this slide a few minutes ago, and I wanted to mention the IPCC. This is the Intergovernmental Panel on Climate Change. There's a URL down here. This is generally accepted as our...
Just stand up, you're probably waiting for you to speak.
Yeah, I think so.
Is that good?
Yeah.
It's gonna be hard on me.
Stay over
Being
here.
left-handed. So really great source of information. This is in a way it's grassroots. It's under the umbrella of the United Nations, but scientists like myself, Julie, many other people contribute to putting together sort of a compendium of the state-of-the-art in where climate science exists. About every 6 years, volumes like this are produced, both talking about the science of climate change as we understand it as of, in this case, 2013. There are other working groups, in addition to people talking about or looking at the physical science, thinking about mitigation impacts and even social justice for different inequalities in terms of who's being affected by climate change. So as of 2013, this was our state-of-the-art thinking about what sea level might do in the future relative to the past. And this is sort of an important slide because it sets up the rest of the talk. So there's a time scale here, and this is going back to the year 1700, so this is years, common era years, going out into the future. So there we are today, roughly, right there. So all of these noisy data are tide gauge information. It's people who go out, people like Julie, geologists, trying to reconstruct ancient and past sea level rise. And the basis, the consensus is that over the last 100 years or so, sea level has been rising at a rate, on average, of just over 1 millimeter per year. And that doesn't sound like a lot. And what's really important to understand is since about 1990, we have noticed that that rate of sea level rise has been accelerating. It's now over 3 millimeters per year. So just since 1990, we have gone way beyond the average rate sea level had been rising over the last century or so. So once you get to the year, well, today, we're measuring sea level as of today, where do these lines come from? And that's what we're going to be talking about. How can we say something about what sea level might do in the future? So we could just sort of project today's sea level rise, that 3.4 millimeters per year, roughly an inch per decade, right? Doesn't sound like a lot going out into the future. But you see that there's a range of estimates into the future, and that's what we're going to talk about. So the worst case scenario, as of 2013, right here, this red line, roughly 1 meter. So, something about like this, higher sea level than today, in terms of the global average. Okay, so where does that sea level rise come from? So, over the last century, it's mainly come from this. The oceans, it turns out, have been absorbing about 90% of the extra warmth that our planet has in terms of heat content. So greenhouse gases are driving atmospheric temperatures up, but the oceans are feeling that, and the oceans are warming, and that's absorbing the bulk of the heat. And so the oceans are warming, and they're losing their density, and so they're taking up more volume. So over the last century, the bulk of sea level rise, that 1.2 millimeters per year, was coming from the ocean warming. Okay, now you've probably all heard about glaciers all over the world receding. You see these dramatic pictures of glaciers in the Alps people used to be skiing on 30 years ago, and the glaciers don't exist anymore. And that's true. Glaciers are receding. And this has been the biggest contributor to sea level rise over the last century. The glaciers number 2. But this is really an important thing to understand, is that all those mountain glaciers all over the world, if you add up all the ice in the mountain glaciers, only worth about that much sea level rise. So mountain glaciers aren't going to drown our global coastlines and our global cities. It's these things, it's the big ice sheets, and that's what I've been really interested in trying to understand what they might do in the future, because there is so much ice locked up on Greenland and Antarctica that if all that ice went into the ocean, global sea level would rise on the order of hundreds of feet, right? Really different scale. Okay, so just for perspective, this is a little dark. Sorry about that. But there's Greenland up there. This is, this is the territory Julie likes to work in. And I've spent the bulk of my career focused on this thing down here. This is Antarctica, the Antarctic ice sheet sitting down there on the Antarctic continent, which is really different from Greenland, as you'll see in a moment. Okay, so we have these two big polar ice sheets. And I should just back up by reminding you that Greenland is big. It has enough ice on it so that if all that ice were to go in the ocean, sea level would rise about 7 meters, about 23 feet. Antarctica is about 10 times bigger in terms of how much ice is locked up down there. So it's a really, it's a big beast in terms of ice volume. Today, we are very carefully measuring changes over both Greenland and Antarctica, and we do it two ways. There are many ways we do it, but the two main ways we're doing it is we fly a very sophisticated satellite that circles the Earth, goes over the ice sheets, and it's measuring gravity. And it's just seeing very subtle changes in the gravity as it goes over Greenland and Antarctica, and it produces data like this. And where it's showing us is actually where in Greenland we're losing mass. So anything in red, ice is going to the ocean, and in Antarctica, it's interesting. Some blue, parts of Antarctica might be gaining a little bit of mass, but you see this little concentration of red. Antarctica is only losing ice today in terms of a real appreciable amount of ice in this really concentrated little spot right here. Greenland, it's much more widespread, and it's over the flanks of the ice sheet. You're going to see why we actually, even though today Antarctica doesn't look like it's doing anything as scary as Greenland, I think this is what we really actually have to worry about in the future. This is actually the amount of ice, just shown as a time series since 2002, that both Antarctica in red and Greenland have been losing in terms of mass. They're huge numbers. These are in units of gigatons. A gigaton is 1 billion tons. And a ton, is 1,000 kilograms. These are huge numbers. Okay, blue, Greenland, red, Antarctica. It looks like Antarctica isn't doing that much compared to Greenland. Both of the ice sheets today are contributing to sea level rise. Greenland, more so, faster than Antarctica. But it's something, you don't have to be a statistician to see that these are not straight lines. Can you all see that they're almost like banana shaped? They are curving. So the loss of ice mass is accelerating. This is non-linear. If they were losing ice by the same amount every year, this would be a straight line. This would be a straight line. So there seems to be something potentially going on. Okay, again, these visuals are really great. Antarctica, right, it had been out of the picture, even for the sea level scientists, up really until about 15 years ago. We were all really focused on Greenland because that's where the changes seemed to be happening. That's where most of the ice loss was happening. Antarctica is just so big in scale that even a little percentage of ice loss from this ice sheet is going to have a big impact. Okay, now to say something about the future, we need two things in general. In terms of the climate science that the IPCC and policymakers are relying on today. We need sophisticated computer models that actually simulate the physics of the climate system and the ice sheets and the ocean. But even if we had a perfect model that represented the physics of climate perfectly, thinking about the future, we still need to know something about what we are going to do in terms of policy. And it mainly comes down to these greenhouse gases that Julie just talked about as being important for the future trajectory of climate and temperature. So where do those come from? Okay, so the climate models are being developed. It's about a 6-decade history now of numerical computer climate models being developed at national laboratories like the National Center for Atmospheric Research in NCAR, where I did my PhD and postdoctoral work. Many labs around the world. There are roughly 30 modeling groups developing these climate models, and they are basically, and I'll just get this animation to, it's a little dark. You might be able to make out, this is water vapor in the atmosphere. You can see the trade winds. The trade winds are moving this way, You can see water vapor in the little red bits are rain. These are essentially global scale weather models, literally the same physics, and in some cases the same sorts of models that we use literally for our daily weather predictions, except scaled up to the entire world. So for 60 years we've been developing these things, we're testing them, we're trying to see where their problems are, we're refining them, and then what we do is we run them for the present day, okay? We run them for the past to see if they can recreate some of the ancient climates that Julie works on. And then once we have confidence in that, we can start to run them into the future. So we need some information about what we are going to do in terms of policy to be able to run these models, because the input that they need, the main one for the future, are what greenhouse gases are going to be like. So really interesting sort of connection between economists, people who work in policy in the energy sector. They get together, sometimes as part of the IPCC, and they think about what different trajectories global population might take, what GDP might do, what's China going to do, what's India going to do in future decades. And then they think about these different scenarios and think about different combinations of different nations using different percentage of solar, developing more hydro versus sort of a more fossil fuel-based future economy. And then at the end of the day, they come up with these different scenarios. And they have been, today we call them the RPCs, the representative concentration pathways. And I wanted to go through that because you're going to see what the future might look like using an alternative set of RCPs. One like this one, this green curve, where carbon dioxide levels just maybe surpass 400 parts per million, the Pliocene that Julie just talked about, and then they actually start to go down toward the end of this century, versus something like this, the blue curve, which is more of a business as usual. So taking current rates of growth and GDP, assuming a fossil fuel intensive future, the blue curve, okay? And we'll look to see what climate does in the future based on that. Okay, now one thing that we have been missing in terms of sea level is that the fancy sophisticated climate models, so that animation I showed you with the winds blowing that we've been working on for more than a half a century, they have not included, up until now, the physics of the ice sheets. So in those models, you can run them out for thousands of years and the ice sheets just sit fixed. They don't move, they don't melt, they don't go into the ocean. So what I've spent almost the last 2 decades now working on is actually building this component of the climate system to put into those climate models. And there's a group here at UMass, and I work with a close colleague at Penn State University to develop those. Okay, Antarctica and Greenland, fundamentally different. And the main reason is, and it's really plain as day. Okay, these maps, there's Greenland, there's Antarctica, these are just bathymetric maps. It's topography, it's a topographic map. Everything that's green or yellow is land that's actually above sea level. Okay, so if you look at Greenland, so this is like a view of Greenland if you had X-ray vision and you were able to look through the ice sheet, it would look like this. So everything that's in blue, you can see in the center of Greenland below sea level. In part, that's because the ice sheet is so thick, it's pushing down on the Earth's crust, and it makes that sort of scooped out hollow. Now, if you look at the edge of the Greenland ice sheet, you can see green around the edges. The edges of the Greenland ice sheet are actually on land. So it's, in most places, it's ice actually just sitting on land with a little fringe of land around the edge. So most of the melt that we just saw, both in one of my slides and Julie's, with the red around these edges, that's melt literally just from the summers now being so warm that the surface of the ice sheet is melting and running off into the ocean. Okay, now, Antarctica is a really different beast. It's like the opposite setup. Instead of the blues just being here isolated in the center of the landmass, you can see the blues are all around the edges of the continent. The ice sheet around its edges are actually sitting way below sea level. So the bottom of the ice sheet here, all around this area, there is about 3 kilometers thick ice sitting on bedrock that is literally, in some cases, about 1.5 kilometers, more than a mile below sea level. And I'll show you what that looks like in a little cross-section. Now, this is a sort of famous quote in my field by Bob Binchadler, and Julie knows Bob, really well-known NASA glaciologist. He likes to say, ice hates water. And that's what makes Antarctica really special, because the edges of the ice sheet come right out to the ocean, touch the ocean, are in contact with the ocean, and there's a big thick part of that ice that's in direct contact. Oh, that's not good. That's okay, I'll come back up. Is it back up?
No. Should I plug it in?
No, I think it's going to be... Okay, cool. Sorry. Matt's letting me down here. Okay, so this is a nice diagram. This is what a lot of the Antarctic ice sheet looks like. The ice is up here, the big bulk of the ice sheet is off to the left, and the ice is flowing toward the ocean. And so it's not really showing up here. If you follow my finger, this is the bed. This is the bottom of the seafloor. And right about here, right where my finger is, actually right where that line is, I can't even see it, the ice sheet is reaching the ocean and it's starting to float. And so there's this big long extension of the ice sheet that's actually floating out into the ocean in direct contact with seawater. This piece of the ice sheet is typically over 1 kilometer thick, 1,000 meters thick, more than 1/2 mile thick ice. And it is all just exposed to seawater below. So as I told you a few minutes ago, the ocean is absorbing the bulk of the heat that we are adding through the burning of fossil fuel. The Southern Ocean is the fastest warming body in terms of the bulk of the ocean that is absorbing that heat. So we are warming the Antarctic waters that are in direct contact with the ice sheet. Okay, now models of what Greenland, and I'll show you a few more animations of models over Antarctica. These are model simulations of the Greenland ice sheet, mostly being attacked again by warm air temperatures on top of the ice sheet, because Greenland isn't in direct contact with the ocean. So here's 500 years into the future in a scenario where we're dumping a huge amount of fossil fuel into the atmosphere, or CO2. Even after 1,000 years, the bulk of the ice sheet hangs in there. We think Greenland's actually a pretty tough ice sheet. It's really Antarctica that would come to worry about. And in part because of the sorts of information that Julie goes out and hunts for. These are, you can see them plain as day, these are really nice oysters. These would literally be, Wellfleet, Katuitt oysters. Same species in some case. In some cases, they're covered with barnacles. We can go out and find these deposits. We date them. In this case, 3 million years ago. This is the time that Julie talked about, just before the Northern Hemisphere started to dive into the onset of the Northern Hemisphere ice ages. Okay, they're found 22 meters above sea level in South Africa. You find sediments like this all over the world, 27, 28, 30 meters above sea level. Okay, that sea level rise above today would have to come from the polar ice sheets. That's a long time ago, though, 3 million years ago. Here's something a little closer to home, 125,000 years ago. So today we live not in an ice age. Obviously, there isn't a big ice sheet sitting over the library today. There was 18,000 years ago. If you go back a little further in time, the climate was similar to today in New England. 125,000 years ago, we call it the last interglacial, as opposed to this interglacial that we live in. And here are these are in the Seychelles in the Indian Ocean. My colleague Andrea Dutton is standing on a 125,000-year coral reef. It's 8 meters, so almost 30 feet above sea level. 8 meters, 30 feet above sea level in the Florida Keys. It's an ancient coral reef. So we know that the ice sheets are sensitive. Now, why we care so much about Antarctica, there's something else really interesting. The ice sheets are so big that they actually change gravity on the surface of the Earth. And if you change gravity on the surface of the Earth, it changes where the ocean's surface likes to rest. So Greenland, big ice sheet, it's actually pulling water toward itself today. So if you start to melt Greenland, it's losing its mass, and it loses its pull on the ocean. And this is really kind of a weird thing to get your head around. But if you take ice from Greenland and put it in the ocean and spread it out over the whole ocean, the loss of mass in Greenland's reduction in that pull on the ocean toward itself, sea level drops around Greenland. All of this blue area is a drop in sea level, even though there's water going into the ocean and the global average is going up. Okay? So one thing that people don't often appreciate is it actually really matters where the future sea level comes from. Is it Greenland or is it Antarctica? So this blue, the boundary between the blue and the yellow is the 0 line. So this is roughly Nova Scotia. You could be in Halifax, Nova Scotia, and the entire Greenland ice sheet could go into the ocean, and the global average sea level would go up 7 meters, and you would be standing down at the beach and not even know it. Sea level wouldn't change. But then as you start to go far away from Greenland, instead of 7 meters of sea level rise, you might see 9 meters, more than you expected. So the trouble for us is that Antarctica is the opposite story. If Antarctica loses mass, close to Antarctica, sea level actually drops, but sea level rises higher, far away from the ice sheet. And you see these dark reds? This is, well, it goes up to 140% of the sea level you expect if it comes from Antarctica. Okay, the coast of California, about 125%. Boston, about 130% of the sea level rise you would expect if the sea level rise is coming from Antarctica. So that's another really important reason why we've been developing models of the Antarctic ice sheet. In this case, this is a simulation of the ice sheet using one of our ice sheet models from 400,000 years ago to today. Now, okay, so why are we using these sophisticated, computationally expensive models to run the model in the past? The reason is, and I think you might have picked up on this from Julie, is that this is how we test the models. We run them in the past to the present day to see if they capture the changes in sea level and in the ice sheet that the geologists are beginning to understand. Okay, does that make sense? We would have no confidence in what they're going to say about the future if they couldn't replicate some of the changes we see in the past. So literally after 15 years of work on this particular model, we started to feel comfortable enough to see what it would do and say about the future. Okay, so this was the paper that Simon mentioned earlier. It's almost been a year now. It got a lot of attention, and the reason why it got so much attention was that what we did was we ran this new Antarctic ice sheet model that had been, after 10 years of trying, it was the first time we got the model to simulate past changes in sea level that we felt good about. And then we applied the model to 3 different future possible policy-driven greenhouse gas scenarios. One, where we start today, when we actually ran the model all the way out to the year 2500, this so-called RCP 2.6, which is a scenario where in the year 2020, we go to near 0 increase in global emissions, and by 2080, in that scenario, we're actually pulling CO2 out of the atmosphere. And I'll maybe hint at that in my last slide. Then we looked at sort of a worst case scenario, business as usual, fossil fuel intensive future to see what the ice sheet would do. And then we ran one intermediate case. And what was really eye-opening to everyone was that we found that we were able to produce a meter of sea level rise just out of the Antarctic ice sheet alone. Now, the old projections that I showed you in my first slide said 1 meter of sea level rise is sort of the high end of what we might expect in the future. That assumed that Antarctica would not do anything. that it's so cold, it's a polar climate, so the meter of the IPCC's estimates did not include anything from Antarctica. So this essentially doubled the worst case scenario for the future projections of climate change. Okay, so the phone's running up, the phone's ringing literally day and night, interviews, BBC, it was really crazy, but it was really interesting because what everybody wanted to focus on were these numbers. Oh my God, sea level is going to be 2 meters higher than today. But the press did not talk about this, that the aggressively reduced future emissions scenario produced almost no risk of Antarctica being a major contributor to future sea level rise. And it was really interesting just to see how the press kind of handled that. This is what it looks like. This is the worst case scenario. Time going here. So we back up, we start running the models in 1950. So we can see if they do a good job from 1950 to today, where we have observations, and then we just let it do its thing. Here we are in the year 2100, and you can see, remember, this is an ice sheet sitting on a continent the size of continental United States. So it's a really dramatic, dramatic change. Absolutely global changing in terms of what our coastlines would look like from space. The other really interesting thing about this was, it turned out that the oceans are important, but you're going to see red appear on the surface of the ice sheet as it's retreating, and this is the amount of meltwater from the warming atmosphere over the ice sheet. So Antarctica, regardless of what the ocean does, eventually it's going to start to behave like Greenland, where it's even just going to start to melt from the top down. But again, it's a much, much bigger ice sheet. Okay, the implications are, going back to this slide, the IPCC's estimate of what the future might look like. It does something like this. It would put us literally almost off the top of the screen if we're right about this. And I am literally, since this paper came out, I've been doing nothing but trying to prove myself wrong about this. And so far, I've been able to maybe think about ways to slow things down a little bit, but we're still feeling pretty good about the results. Okay, so what does this mean for us locally? The city of Boston picked up on this. Marty Walsh, very concerned about the future of Boston in terms of sea level rise. And he got together with some Bostonian businesses, the so-called Green Ribbon Commission, and they sponsored some work actually looking at the implications of these new sort of emerging science on Antarctica and what it means for Boston. These were the numbers that we provided the mayor's office. So this would be the global impact of these new simulations in the RCP 2.6, the intermediate case, and the worst case scenario, the 8.5. And then you don't need to really see the numbers, but you can see that Boston is higher than the global average. Again, that's because Boston is sitting in a really bad geographic location because of this gravitational influence. We've done some statistics on little tweaks to the model. You can tweak the model physics a little tiny bit and run thousands of simulations and look at the statistics of that. And what we found was there's a 10% probability in the model as it exists where sea level could reach more than 2 meters by the year 2100 in Boston Harbor. Really great website if you don't know about it. Julie showed a slide from this. This is Climate Central, and they're really sort of at the forefront of outreach in terms of showing the impact of what changes like this mean in terms of neighborhoods. So you can go into Climate Central. This is their sea level risk mapper, and you can plug in a zip code. And right, as Julie showed, you can slide this bar around. This is in meters, not feet. This is what the 2 meter mark looks like for Boston. So everything in blue, below sea level, not accounting for storm surges, nor'easters. This is just the background sea level. So much of downtown would be flooded. The green is your sort of, there, it's a little spotty. So even Logan is potentially in a bad place. That has sparked some thinking about massive engineering projects in the city of Boston. Like this is from a recent Boston Globe article where people are really beginning to consider infrastructure changes comparable to what the Italians are doing in Venice, what's been going on in the Netherlands, the Thames River in London, and so forth. If you don't care so much about Boston, but you like to vacation on Nantucket, again, you can look at that. I mean, it's a pretty bleak story, particularly for some of these salt marshes, the ponds behind the barrier island or barrier bars really doesn't look good. Now, another thing to think about is that in these scenarios, it's not just about how high sea level gets, it's how fast the sea level is rising. So over the last century, sea level was going up on average about this much per decade, and in these worst case scenarios, we're talking about inches per year sort of rates, more than 2 centimeters per year by the year 2100. Okay, California is doing the same thing as Boston. They're concerned. I'm right now literally working for Jerry Brown and looking at the implications of this and trying to give policymakers a feeling for the uncertainty in this kind of climate research. They're very motivated, obviously, for the same sorts of reasons. California is looking at multi-billion-dollar infrastructure projects all over the state, and they want to know if those locations are going to be okay. So this is probably not going to play.
It's called COP21, which is the 21st Conference of the Parties to the UN Framework Convention on Climate Change. It takes place in Paris from the end of November to the middle of December, and it will feature representatives from 196 countries, including many of their leaders. The Paris negotiation hopes to secure 2 things. One is a new deal on climate change that will limit emissions of carbon dioxide that scientists say are really driving temperature rises around the planet. The other thing it aims to do is to change the nature of how we do business on this planet, which is how we produce, how we farm, how we make things, and how we consume it. This is a long-term goal. It's about changing the very nature of progress. If they manage to do that, that'll be one of the most significant things we've ever achieved.
So the Paris Agreement, I'm sure you've all heard of it. So I think there are 197 nations that are involved in Paris, and about 140 have now actually signed agreements, like Obama did more than a year ago, in saying what every one of those nations is intending to do in terms of reducing their future emissions. These are the so-called INDCs, these intended nationally determined contributions. Okay, now it's really important to understand that even if you took the existing Paris Agreement at face value and added up all the nations' goodwill, that would probably get us to, we think, about 3 degrees Celsius temperatures warmer than at the beginning of the Industrial Revolution, as opposed to the sort of language that the Paris Agreement is really aspiring to, where they're talking about limiting warming to 1.5 or maybe 2 degrees. So even the best case scenario as it stands, we're still looking at maybe 3 degrees of warming by the year 2100. Now, I was thinking a year and a half ago that, okay, we're heading down the right road with agreements like this, internationally coordinated agreements. Okay, this is the roadblock right now. You know, you've all seen the famous tweets. This was a new one to me, and I didn't fact check it. It could be fake news. This very expensive global warming bullshit has got to stop. So this rollback that you heard about on Tuesday of beginning to roll back and push back on the existing Obama legislation is a problem. And when you think that it runs so deep that the head of the EPA is still saying that he's not willing to admit that humans are contributing to climate change, this is going to be a tough road. So this was Obama's plan. These are the U.S. intended nationally determined contributions. And this black line was our emissions every year up to the year, you know, to today in thousands of megatons. So I would have put this 5, 6, 7, these are gigatons of carbon. They're really, again, big numbers. So if you took Obama's Clean Power Plan that came out a few years ago, okay, that takes this piece out of where we would have gone in business as usual sort of case. Okay, the Clean Power Plan the Climate Action Plan, more recent legislation, sort of put us on track to what is the US INDC, and what now the international community is beginning to call already, and this just came out at climateactiontracker.com. This is associated with the Potsdam Climate Institute. These are scientists, academics. They're calling it the Trump effect. So this is where Obama was trying to get us, and this is where we will end up if we follow what Trump is considering. Now, I know he hasn't decided on whether or not he's going to pull out of Paris or not. China is in, regardless of what we do. I'm not sure where India stands as of today, but you can see it's really important. So this is the last slide. And so now what we're starting to do is we're beginning to get a little more confidence in looking at these future projections. We cannot just look at the RCP future scenarios from 5 years ago. We can start to think about the implications of the Paris Agreement on global emissions in the INDCs to see what might happen into the future. And these are simulations of the ice sheet looking into the future, 2020, 2040, going out to the year 2100. This is if we reduce emissions enough in black to keep global temperatures below 1.5 degrees C. That's the most aspiring Paris Agreement case. The blue line, 2 degrees. Not too much happens to Antarctica. And then this is really interesting, 2.7 degrees. So this was the number I told you is where the Paris Agreement stands today. It's a big difference from the aspiring target. And then this would be more the sort of Trump effect in going down a business as usual path. So we really want to know, with the work, and this is what we're doing here at UMass, is this a real threshold? We really want to know. We need to know that. It's policy relevant. But even if we're not quite right about the details of exactly where that threshold is, you'd have to think that it would be wise to caution on the conservative side and say, okay, the science is getting better, it's not perfect, but even approaching the current best intentions of the Paris Agreement, it still puts us in dangerous territory. So, this is the good news. I hope that you got that out of today, is that, the horse isn't out of the barn yet. There's still room for policy to have a big impact. And that's why Julie and I were motivated to come today and to keep trying to get the message out. And hopefully there'd be students here to have long careers in front of them to think about helping us get down here rather than up here. Okay, thank you.
Time for a couple questions? Sure.
So Solomon mentioned UMass Lowell having some models that different than this, or is this tied in with that?
So theirs would probably be more on the climate side in thinking about the temperature. So we take the atmospheric models, and that's where we get our atmosphere over the ice sheet. So this is really looking at the ice sheet physics and the ice sheet's response to the warming world, sort of for the first time, rather than those parts of the system not being accounted for. So it's pretty new territory.
Do you think that it's pretty safe to say that just because we've got a lot of the industry that is carbon intensive, that creates emissions in the northern hemisphere? I mean, do you believe that between your two sciences and your experiences, do you believe that that is what's driving this change now in the northern hemisphere? It's just because the carbon is concentrating here, not circulating down below the equator? I mean, what is that?
The atmosphere is actually very well mixed. This is why you can measure the CO2 in Mauna Loa in Hawaii and in Antarctica and get very similar numbers. So the atmosphere is very, very well mixed, and so it's having a more global, the impact is global because of that mixing. It's like, we have a volcano goes off in the Philippines. It only takes about 2 years for that volcanic ash to be detectable all over the world. So our atmosphere mixes really well.
Is the quantity of float ice in the Antarctic increasing significantly?
Or just sea ice?
The sea ice?
The quantity of float ice.
It's the mass of the floating ice is thinning. in fact, it's the floating ice that's thinning faster than any other part of the ice. And what that's doing is the part that's just floating, it doesn't contribute to sea level when it's lost.
Right, that's what I was getting at. I mean, that's why I was saying is the quantity increasing, because if it's increasing, you would be getting...
Great question, but so why we care so much about looking at the floating ice? Not for sea level directly, but where the ice flows out into the ocean, if it bumps into something, and it does in many places, it slows the flow of ice from land, the land ice that's going out into the ocean. So as we're losing the float ice, it's making the ice sheet behind it respond faster and flow out into the ocean faster. So it's an indirect bad thing.
It's holding ice back.
It's holding the ice back.
With the changing of the gravity based on the density and the mass of the glaciers, does that change the axis at all of the planet?
Yeah, it
And
does.
if so, does that change
Pretty
the
good question.
temperature?
So those maps I showed you, they account for two things: the impact of the gravity and the impact of the change in the Earth's axis of rotation, which moves a little bit. So those are all in these calculations of these sea level maps. We call them fingerprints now, and you can look at a change in even literally one little corner of an ice sheet and see what it does to the map of sea level. It's pretty cool. Yeah.
Hi, I'm a political science major here, and you spoke a little bit about Scott Pruitt. I'm just wondering, in terms of policy, if Trump is able to eradicate the EPA, which he's trying to do, it's like a budget proposal, is there another agency that you know of that has governmental influence like that, or will we have to wait for the administration?
I don't think so. I mean, the EPA really is looking at what we call, pollutants in the atmosphere, and they really helped us get rid of, for example, a nice success story was leaded gas. I mean, when I was learning to drive, we went through that transition from leaded gas to non-leaded gas, and it's because we were measuring so much lead in the atmosphere, we were able to actually, change it pretty quickly. It was successful. That was the EPA, and the EPA was basically decided that this is a CO2 in excess of normal glacial interglacial cycles is in fact a pollutant, and therefore they were tasked with regulating it. And so I don't think any other agency has that.
Do you think it's valuable enough that he will be able to actually keep it back?
Well, not if we work at it, all of us.
The other thing is that the Supreme Court has ruled that CO2 is a pollutant, and the EPA is required to take care of that. So I don't know how that's going to get dealt with in the long run.
Good point.
So the states, like as you could see, people like Jerry Brown, or he insists, he reminds us often, even the climate community, that I'm in control of the 5th biggest economy in the world. And if you look at so I showed you the Trump effect on going back against the Clean Power Plan and the Climate Action Plan of Obama. You can put a little piece back if you look at California by itself. And so at some point, I'm thinking that the states are going to have an important role to play going forward. Pruitt's in a lot of trouble. I don't know if you saw the news yesterday, but he's under investigation for potentially lying during his confirmation hearing. So we'll see how that all plays out.
There was a question in the back.
How do you see the density of the concentration of melting in the Antarctic changing within the next 100 years?
For sure. Yeah. Well,
How so, or like how would it expand from looks like near the Ross Ice Shelf?
So this is ground zero. We think right now is this little piece of the ice sheet, right? It's right here. So this is the dark blues are thicker ice, and you can see where the ice sheet is really thick. And it's thick here, and it's thick here, and here, and here, because that's where the land is really depressed, really, really thick. This, in one of my first slides, there was a big red blob that showed where the ice sheet is responding today. That's right here. There's a glacier. It was my opening slide, actually, and I didn't because I was still trying to get set up. And this is the glacier that's flowing in. This is a satellite image of that one little piece of the ice sheet, and there's a big glacier right here. It's from here to here. It's called the Thwaites Glacier. This is 120 kilometers wide, right, for scale. And this is where the ice sheet is losing its mass the fastest. Right now, today, is literally right here. So this ice surface is going down, and this edge, this is open ocean, this is sea ice, and this used to be the floating ice, the thick ice shelf that used to slow the flow of the Thwaites Glacier as it was going into the ocean. So you can see that that ice shelf is all broken up today. It's literally breaking up. We're watching it break up every year. And this edge of that glacier is, the ice here is 600 meters thick, and it is backing up 1 kilometer a year right now. And that leads into, it goes back about 200 kilometers, like back where Julie is. And where Julie is standing, it's 2 kilometers thick where Julie is standing. So this is what we're watching closer than any other part of the ice sheets, either Greenland or Antarctica. And the US National Science Foundation and the UK's equivalent, NERC, just got together and launched a $26 million program to just study what's going on right here, literally next year. They're trying to get helicopters to put to meteorological stations on the ice right here, and they're going to try to get in with a ship. It will launch literally like submarines, automated like drone submarines, right up against the edge of the ice sheet to measure the temperature. So this is kind of ground zero right now in science.